This is a term that you have probably seen and looked at and covered before, but don't remember because it was mentioned like once for a minute. The implicit form of a function just means that it's not y in terms of x. It's things like x and y on the same side. And so if instead of y equals 2x squared minus 3x plus 4, we had 3x squared minus 2y plus 4x, y equals 7. This is an implicit form of a function. And so it's easy to take the derivative when we only have one variable to worry about. But what we're going to look at is if we have multiple variables happening on one side on both sides of the function, then how are we going to take the derivative in that case? So we need to be able to find derivatives of equations. To do so, we must understand what dy dx actually means. Dy dx says that we're taking the derivative of y with respect to x. So in other words, we are taking derivatives with respect to x of some function. And we haven't had to worry about that in the past because all the derivatives we've taken have involved just a variable. We haven't had to ask, well, which variable were we taking as that derivative in terms of? Because it's only in terms of, there's only one variable there, so we only need to worry about in terms of one variable. And so technically, we should be writing like a dx over dx. But dx over dx is just going to be 1. And so we usually don't need to write it. But when we take derivatives with respect to x and then other variables crash the party, then we need to worry about writing that d by dx term. So we are going to differentiate these with respect to x. So d by dx of x cubed is 3x squared. Since we're taking the derivative with respect to x, that's all we need to do. But on the next example, if we're taking the derivative of y with respect to x, that's when we need to worry about doing these. So we can still take a derivative of y cubed, which would be 3y squared, but then we need to say we're doing it with in terms of x. So we need a dy over dx. That's our answer. So it's just adding that dy over dx that is kind of there but invisible. Kind of like how when we write x, we really mean 1x, but we don't bother to write the 1 because it's implied, and we're lazy and we want to save not having to write the 1 every single time. There's really a dx in here. We just never write it because we don't need to. It's just 1. But if we're taking it with respect to another variable, then we need a dy over dx. Next, derivative of x plus 3y. Derivative of x, just 1. Plus derivative of 3y is 3. But now we're taking a derivative of y. So we need to write a dy dx. So we didn't need to write it here because we're taking a derivative of x, but over here we're taking a derivative of y, so we need a dy dx. So we need that dy dx anytime we're taking a derivative of y. If we're taking a derivative of x, it doesn't need to be there. So that means if we have something like xy squared, well, xy squared is a product rule. So we are going to do first times derivative of the second, Derivative of y squared is 2y. Do we need the dy dx? Yes, we do, because we just took a derivative of y. Took a derivative of y squared would be 2y, so we need dy dx attached to it. Plus second, which is y squared, times derivative of the first. Derivative of x is 1. Do we need a dy dx? No, because that's a derivative of x. We didn't take a derivative of y, so we don't need the dy dx there. So it would be, that is a 1. So if we wanted to simplify it, we could have a 2xy dy dx plus y squared. And dy dx is what we'll eventually want to know, because that would be the derivative. That would be finding the derivative of y with respect to x. So our goal is going to be eventually solving in terms of dy dx. So here's what we're going to do in order to do that. That's the idea. That's kind of the new idea behind implicit differentiation. Here's how we're going to solve an implicit differentiation question. What we are going to end up with is something that is solved as dy dx equals. So the way that we're going to do that is we're going to differentiate everything with dy dx with respect to x. So that means if there is a derivative that we're taking of y, we need a dy dx attached to it. That's step number 1. Then step number 2 is we are collecting all the dy dx terms. We're going to group them together on one side. We're going to group everything that doesn't have a dy dx and move it over to the other side. So that, if you remember kind of a common factor idea, we can take that common factor of dy dx and factor it out of the whole thing and then just divide. And then we have dy dx by itself. That's going to be our way to get dy dx by itself. Let's take a look at it in action. So step 1, it's writing out in the steps. Step 1, we need to differentiate both sides with respect to x. So our first step, we have y cubed plus y squared minus 5y minus x squared equals negative 4. So first we're going to take our derivative. Derivative of y cubed is 3y squared. Oh, I took a derivative of y, so I need a dy dx there. Plus derivative of y squared is 2y. Oh, I took a derivative of y, so I need a dy dx there. Minus derivative of 5y is 5. Oh, I took a derivative of y, so I need a dy dx there. Minus derivative of x squared is 2x. Oh, I took a derivative of what? No, I didn't. No dy dx. Equals derivative of negative 4? 0. Does that have a y on it? No, it doesn't need a dy dx. All right. Four terms. There is one imposter among us. Which one? The negative 2x. Boot it out. To the other side of the equation. So anything, sometimes there's just one term. Sometimes there's multiple terms. But anything that doesn't have a dy dx on it, kick it out to the other side. And now all the dy dx terms are happy in their club over on the side now that they've kicked out the one that doesn't belong. So now all these have a dy dx in them, so that means the dy dx can come out. This is step 3. Times, we got a 3y squared, we got a plus 2y, we got a minus 5. 2x is still hanging out on the other side. It's happier over there anyway. It doesn't care. Totally doesn't care. So we have dy dx times all of this, so we're just going to divide by all of it. All right, and then I need to, this is going to wind up here. So that I have the room. This is step 4. We just have dy dx by itself equals 2x over 3y squared plus 2y minus 5. Plot twist, the 2x wound up on top at the end. So who's really the winner? All right. Equation of the tangent line at the point 1, 1. So we have derivative of x squared is 2x minus derivative of y cubed is 3y squared. Oh, we took a derivative of y, so we need dy dx equals 0. Everything that doesn't have a dy dx gets kicked out. Normally, I'd factor everything with a factor everything out that's got a dy dx in it, but there's only one term there, so we're all set. So to get dy dx by itself, all we need to do is divide. And so our final answer is dy dx is going to equal negative divided by negative is going to be a positive 2x over 3y squared.
Well, wait, there's more. Oh, did I take it from you? I'm sorry.
There will be more.
Okay.
Yes. I want equation of the tangent line. At the point 1, 1. dy dx equals x is 1, y is 1. Two times 1 is 2 over 3 times 1 squared is 3. So 2/3 is dy dx. So we have our tangent line is y minus y coordinate equals the slope times x minus the x coordinate. Our point is 1, 1. So x is 1, y is 1. And then our slope is what? the 2/3 that we found over there. There we go. That's our equation of the tangent line. So the different part about the tangent line stuff there is that since dy dx is going to have both x and y on the same side, we'll need to plug in, usually we plug in for x, and then get out our y prime. But here we need to plug in for both x and y since we have both x and y on this side of the equation. Questions on that? Let's see. Let's do one more. Next page. This one I'll actually have you try on your own. You should have all the tools to try this one on your own. And those in my Tuesday, Thursday group, I'll expect this done when you come into class tomorrow. We'll talk about it the first thing tomorrow at the start of class.